Alright, this is 2010, number 1. So, based off of this question, it looks like it's a typical drag question. So, in part A, they said that the drag force on an object is represented by CV squared, where C is just some constant, and they want us to figure out what is the terminal speed. Remember, terminal speed is when the sum of the forces equals 0, and that's when it moves at a constant speed. So we have gravity pulling it down. Let's see, do they tell us? I guess it's just M. I guess we're supposed to keep it as mg. And then the drag force going up. So that means mg minus cv squared equals 0. mg equals cv squared equals square root of mg over c. Alright, that's pretty much the answer. Oh, wait a minute. Sorry. They don't want just the terminal speed, but they want to know the relationship between terminal speed and mass. So I'm actually going to rewrite this. I'm going to leave it as v squared equals GCM. So like I said, I want to try and keep my constants all together and then leave the variable by itself. So this is kind of where you want to end it off. You can't end it off here, but this one looks a lot better. So this was 2 points. 1 point for getting this answer. Either this one or this one probably wouldn't hurt. And then 1 point for realizing that the net force equals to 0 for terminal speed. Alright. Moving on, part B has 2 parts. Alright, first part was graph the data and then use the graph to figure out C. Now I'm not going to go into much detail with the graph, but I will say this. So the equation that we have from before says this, showing the relationship between the terminal speed and the mass. Basically, that the terminal speed is squared proportional to the mass. So that means that my data should be mass and velocity squared. Now if you look at the chart, and this is something that's very common, you'll see that there's 3 rows and one of the rows is empty. So what that means is that you have to take one of those numbers and do something with it. You know, you're not calculating something else. You're going to just take one of those other numbers and just either square it or double it or inverse it or something. In this case, you can pretty much either do VT squared or square root of m. Either way works, but they have it as VT squared, and you should end up getting 0.26, 0.38, 0.67, 0.85, and 1.12 for VT squared. And then when you graph the data, you know, you're going to end up getting some line. Looks like this with your data at different parts. Now you have your VT squared here, mass over here. Yeah, you guys should know how to graph data, so I'm not going to go into any more detail than that. But the thing that is in, so here you got points for, let's see. Alright, so you got 1 point for graphing the data so that it becomes linear. It says 1 point for basically doing something with this line. 1 point for including some sort of linear scale on the axes. So basically having it go up by a factor of 0.1 or going up by 1. It's not just like randomly going up. You got 1 point for doing a line of best fit. So not only graphing the data so that it's linear, but graphing the line of best fit. And those are your 4 points. All right. The second part of this is saying use the graph to calculate C. Now, what does that mean? Again, use graph is code word for saying use slope. So somehow we have to use the slope to determine C. Now again, if you look at remember the equation, it was G over C, M. Slope is just the change in VT squared over change in mass, change in Y over change in X. Looking at this equation, VT squared divided by M is the same thing as G over C. So that means that the slope of my line is going to be equal to G times C over C, or C equals G over slope. Again, when you do slope, change in Y over change in X, when you do the slope, you have to choose 2 points on the line for it. It really depends on the numbers. You should get a slope that's about 217. So C equals 10 divided by 217. So your value for C should be somewhere around 0.045 kilograms per meter. Alright, and that's basically it. This was 3 points. You got 1 point for getting the correct units for C, 1 point for realizing how to use slope with C over G, G over C, and 1 point for calculating the slope using the line of best fit. Alright, those are your 3 points. Alright, moving on to C. They want us to graph the speed versus time. And when it hits terminal speed, basically what's going to end up happening is this. I think they say, yeah. So our graph for D, for C is pretty straightforward. It's going to look like any terminal velocity graph. Boom. You got your terminal velocity here, and then it actually does have an ending point for time, so it's going to be T. There you go. And you got 2 points for having a graph that starts at the origin and initially goes up, and a point for basically having the graph looking like this. Now what they asked for in part 2 is basically, if you had numbers, how can you figure out the distance that it traveled? So remember, if you're trying to find distance from a velocity graph, that means area. So all you have to say is something like take area under graph. And that's basically it. And under graph from 0 to T. Another thing that you could say is by taking the integral of the velocity equation, again, from 0 to t. And that was pretty much 1 point, because, it's pretty straightforward. Just say area, and boom, you got your answer. One quick correction. You got one more point in this part with the graph for labeling VT and T. So this was a 3-point question, while part 2 was only 1 point. And then the last part, D, says that they want us to determine the amount of mechanical energy dissipated due to the air resistance during the time that the stack falls, distance y, y greater than big Y. Alright, so you want to think about what types of energies you have. So for here, we start with some initial potential energy. I should say that the total change in the energy is just the change in the potential plus the change in kinetic. The change in potential will just end up being mgy. And then the kinetic will end up being final minus initial. Actually, shouldn't be. Actually, I kind of wrote this a little messed up. Should be negative mgy, because you're losing potential, but you're gaining kinetic. But you're only gaining kinetic up until it reaches this terminal speed. So this is pretty much it. You can even rewrite it so it looks like 1/2 mvt squared minus mgy. Or you can even write it like this. Either way works. And this one was 2 points. 1 point for realizing how to put in the terminal velocity and the height y, and 1 point for realizing that the change in the energy is just the change in both of those types. The one key thing that you had to remember, though, was this sign. You had to make sure that you remember that it was negative because of the fact that you lost energy, you lost potential because it fell down. Alright, keep practicing these problems. If you have any questions, feel free to let me know as soon as possible.